Okay, so what people would like though in a perfect world is cloud flexibility, but for AI, like with the cost savings on on-prem infrastructure. And we're not a cloud company, but we try to give people that have it your way approach to actual physical servers, and it really works out well for in the machine learning and deep learning space. So kind of our core goals are we want to design, we've designed an ecosystem basically that enables an individual to say, I want this many GPUs, I want this much storage. I want, I've got an algorithm that can take advantage of 16 GPUs, or I need 16 GPUs and 16 Connect X6s all connected to one server, or 20 or whatever. And we enable, a user to build those building blocks as they need them, and basically kind of compose up a physical server from really, I would say, simple building blocks, but they're relatively complicated on the inside. But to the user, it's just, an enclosure with storage or, GPUs or whatever. Kind of similar to how the storage world started doing this years ago with storage arrays and stuff like that. They disaggregated the controllers and the disks and the network interfaces, and that seemed to work out pretty well to kind of meet everybody's needs. So we're basically just doing that with compute devices and storage, I guess. Okay, so this is kind of like sums up how the technology actually works. So in a typical world, you've got your servers, all your devices are stuck within them. What we do is we actually break those devices free of the server. So instead of buying a bunch of gigantic servers to fit all your precious PCIe devices, we break those all out into pools that allow you to do things. One, you don't have to buy as large of a server, but then two, now that they're disaggregated from the server, you can dynamically assign them, based on what you're doing. So one of the things that I did in my past a lot was, with AI workloads, people are like, oh, training is, all about, these giant, clusters as large as you can get, and you just, hammer them, and that's what happens. Well, there's this other part of training where you actually have, you're trying to do hyperparameter searching. So you're trying to do a bunch of little tests, running a bunch of small models or models with little data, trying to find good parameters before you go throw the thing on a large cluster. And that's usually kind of a cycle that repeats itself. So having the ability to carve off small amounts of GPUs or storage, ETL, whatever, to different nodes is very advantageous in that kind of a workflow. And that's actually what we enable. So basically, the way it works is we have, our pool of resources, the storage, accelerated, basically co-processors, GPUs, FPGAs, DPUs, and then we have our HCAs or, Connect X6s, Connect X5s, all that stuff. And we expose it via a side channel software interface to the actual physical devices that contain all these, or this physical enclosures that contain all these devices. And then we allow machines to be dynamically created from this whole pool of resources. And what that allows you to do is dynamically create hosts with different profiles based on your need at the time. Or if you don't, if there are some very large customers we work with who, they have just, they're the ones that are just like, hey, I need a machine that doesn't exist today, and I want X number of GPUs and X amount of storage, and I need 16,000 of them. Can you get it to me now? And we're like, yep, we can just compose what you want. So this is just kind of walking through, breaking up the different pools of resources into a composed server. And what's really unique about our stuff, so we are definitely a very hardware centric and kind of very low level. I say our core expertise is around the really the the lowest level of the server. So, the PCIe bus. Go ahead.
Joshua, so the solution, does it require having, are we buying normal servers with GPUs and FPGAs and storage in them, or are we buying separate boxes that just have compute, storage, GPUs, and FPGAs? I'm trying to understand what the physical manifestation of this disaggregated resource pool looks like.
Right. So Sumit will go into that in more detail, but fundamentally, at a high level, the way it works is this. So there is a hardware device. There's kind of two ways you can do it. You've got your base servers. So these can be Dell, Supermicro, whatever, that have basically CPU, memory, and that's pretty much all you need.
A PCI bus or something like that.
Yeah. Yep. So you go buy from your current vendors, and kind of depending on the use case, we have different recommendations. Like if you want to build a really beefy, 16, 32 GPU system with, the same amount of HCAs in it, you're gonna want to go with like a dual EPYC, proc system that's got tons of PCIe lanes coming off of it. And especially if you're doing like training, for instance, where you're going to want, to scale up that node as much as possible. But you can buy whatever server you want. We usually have recommendations based on, the use case. There definitely are kind of sweet spots for different stuff. And then you buy, the other part would be the actual enclosures where the devices live. And then those connect into our Liqid Matrix fabric, which is based on PCIe. So you're just basically disaggregating the PCIe bus that was stuck in this server across this entire pool of resources. And then you can dynamically, create machines. It's kind of like in a network, you have the physical layer and the software layer, or the logical layer, right? So what we do is we actually take that concept and we apply it to the PCIe bus. So this server believes it has a very specific PCIe architecture, even though it has a drastically different PCIe architecture than
physical manifestation. Yeah.
Exactly.
And is PCIe extension, or is it doing that over Ethernet, or how is it?
It's all PCIe. Yeah.
Okay.
So and there's a technology. Actually, it's really kind of what. Honestly, I think it's like our I wouldn't say secret sauce per se, but it's probably one of the most valuable things we bring to the AI space, and that is what's called peer-to-peer our implementation of peer-to-peer. So traditionally, when people think of like RDMA, they're talking about mem copy. So you're like, oh, we do all this over RDMA and everything's so fast and blah blah blah. But really, what they're talking about is we're not doing a mem copy into the CPU. The communication still has to traverse. So let's just pretend here, because I don't have a diagram of this, but let's just pretend that this, in a normal server, let's just say this is a normal server. Let's just say this GPU needed to access this NIC right here. And the way it would work on a normal server is you have to go here, up to here, get routed through the root complex, come back down, and then go over here. Now you're not going to do a mem copy if you're using RDMA. So, that's good. It's not terrible. What we do is we bypass the root complex and actually allow direct communication between, this GPU and this GPU, or this GPU and this HCA, or kind of whatever you want, without having to traverse the PCIe bus back to the root complex. And what you end up with is a communication. So usually with RDMA, you're still gonna, if you have to traverse that tree, you're going to have about half the performance is usually what we see in the field of the performance of our peer-to-peer architecture that allows us to just bypass that. And the reason we're able to do that is kind of like I mentioned, there's this side channel technology that's kind of keeping track of everything and directing the packets where they need to go, instead of that having to happen at the root complex in the server. So,
thanks.
Yep. Cool.
Josiah, are you working with Gen 3, Gen 4, and Gen 5 PCIe, or are you limited in there?
Yeah, so Gen 3, Gen 4 today. we're moving to Gen, I guess 5 and maybe Z. We're still talking about that, but Sumit might actually be able to provide a little color there. One of our
absolutely. Yeah, no, sure. Absolutely. So guys, today we're Gen 3, Gen 4, Gen 5 is coming. Gen 5 will be a 2022 event for the industry in our belief. We'll start to see Gen 5 emerge, and then post Gen 5, additional fabric types will be invented. Things like CXL, industry is contemplating Gen Z. We're already talking about PCIe Gen 6. So our mission is to be multi-fabric and to control all the fabrics out there. So today, Gen 3, Gen 4, Gen 5, and CXL are imminent.
One of the additional benefits of our technology is the ability to dynamically compose resources based on times a day or workloads or demand. Let's say during the morning you have a bunch of data scientists who've carved up a pool of resources, and you have these GPUs that are assigned to a handful of different folks, and they're doing hyperparameter testing and searching and all that fun stuff. Then everybody goes home in the evening, and what you can do is just schedule those resources to be rededicated back to your training cluster or whatever kind of batch processing type system you have. So you can support multiple workloads of the same system. And this is
that where Slurm comes in to this discussion?
Slurm is so we integrate with Slurm and Kubernetes and all that. We don't currently do, and I guess I don't think we should either. We don't do any like QoS or monitoring where we take control of devices and yank them away from servers, just because of the wide variety of applications that are out there that could be using them. So that could be dangerous. But integrating through Slurm and all the other job schedulers and workload managers, primarily it's like Slurm, Kubernetes, I guess your provisioning tools like Ansible and all that fun stuff. But we integrate with those where you can control and compose, using the tools you're already familiar with in order to reassign devices based on jobs, times, workloads, schedules, all the stuff we're used to doing already with all that software.
Okay, thanks.
So this is kind of, I was actually going to go a lot deeper into this, and then I kind of got poo-pooed, but really there's a ton of different things from an AI perspective that being able to right size your system or purchase something today based on a new GPU that comes out or a new technology that comes out and get it into your infrastructure and start using it. There's a ton of benefits from doing that. So I just kind of put this base slide together. I mean, there's a bunch of other things: power, right sizing power. There's like 6 major things, but I'm not gonna go too much into them. I'm just gonna kind of be like, okay, from a very high level perspective, if you just say, so if you like think about it and you're like, all right, GPUs come out in October, right? You can't get a server that is compatible with that GPU unless you go with a DGX until March, May, June, supply chain stuff. It's like probably even longer right now. So by the time you get your server that has, the GPUs in it for your inferencing or your training, you're basically 6 months away from the next latest and greatest thing coming out. And what happens is this. So let's just take a company. So usually like when the next generation of GPU comes out, there's a doubling in performance and a halving in power. That's kind of what we see for cost per watt. And so what most people do, and this is if you're not doing the DGX, yes, the DGX is available right here, but that might not fit. It doesn't fit everyone's workload is kind of the issue. Or one of the weak points, we like the DGX and we're integrating, that NVLink technology and their HGX stuff into one of our systems right now. So it's a great system. But if you're looking at it from a server perspective, what's going to happen is you're going to have, let's just take, company 1 and 2. So company 1, on the y-axis is model performance. Let's just pretend these are like identical companies. They're doing everything the exact same way, and they're competing in the same market. So the purple company, GPUs are released. 6 months later, they get their servers with the GPUs in them, and their model performance doubles. And then same thing happens again, over here, model performance doubles. And they, over 36 months, their model performance ends up here. Just assuming you're, building the next GPT-3 or something like that. But this is basically kind of what you see. Like the plan is keep your training systems going, keep improving performance, keep going around that flywheel, right? Because we all know that's
so
how you
Josiah.
Go ahead.
So my question is, what you're putting in your model here is that people are constantly switching out servers and GPUs. And what I see in the enterprise space more where I'm working with it is I don't see a swap, I see an accumulation, right? I see older model GPUs, newer model, up into the latest and greatest, all the way back to, I don't even remember, like old Radeon stuff, right? So how does Liqid help me handle all of that? Can I still build those servers out of that, or do they have to be homogeneous? Or you tell me.
Yeah. So actually, you can use the same servers you're using today. I wouldn't recommend putting the devices in the server because that defeats kind of one of the values of being able to scale that server up to, the right size for your workloads. So the way it works is this. You can still keep buying your servers from server vendors. What I would recommend is you just start right sizing your equipment and this slide actually doesn't go over it. This is kind of just nothing, you weren't right size. None of these companies were right sizing. None of these companies were optimizing on power, designing or building a node that fit their, model's performance requirements without basically doubling your power bill, which is what we often run into, especially for like the larger clusters. Power is kind of a huge thing. So go ahead.
Can I just feed back to you something that you just said and kind of put it in more concise terms? What I think I hear. Basically, by right sizing, you're able to accelerate time to market of when they can take advantage of the new GPUs, lower their costs, and improve their performance in their model. Is that it in a nutshell?
Yeah, that's it in a nutshell. I mean, and this is just the graph to kind of, assuming nothing changed, day one when the new, A100 DPUs come out, you can drop those into our enclosures because we certify the enclosure based on a range. Well, really, it's based on kind of the max, theoretical we see coming out in the next, 2 to 3 years of devices. So instead of having to recertify a server and go through all the pain and suffering of getting power and cooling right and rejiggering risers and all that stuff, we don't have to do any of that. We're just like and our customers don't either. So if they, the GPU, new GPU comes out, they're like, hey, we don't need for our workload, we don't need as large of a node. We don't need as many GPUs. Great. Don't buy as many enclosures. And you can, do that today versus waiting 6 months to get the server that's certified. And what that ends up doing is killing your training time. So like this wait, this is, like I said, imagine two companies, they don't do anything different. We throw power, cooling out the door. We throw right sizing the system out the door. Let's just pretend these are identically sized systems. What you end up with using our technologies is the ability to start modifying your infrastructure the day new equipment comes out, get it in the field. And what ends up happening is, just imagine this is model performance or compute cycles or whatever performance metrics you want. What ends up happening is you end up moving up the y-axis faster than your competitor, and even if you're not doing anything else. So, and this is an exponential gap that forms here. So, by this point you're up here somewhere, but that's kind of just throw everything else out. If you just look at the way training and inferencing works, it's kind of just kind of a no-brainer, I think, but that's just me. So go ahead.
To clarify, you're saying if your customers keep the same data sets that they have, and they're just upgrading their GPUs that they're training models on, they'll get higher model performance?
In theory, yes. So, I mean, that's kind of what the scaling hypothesis says, is as you increase the size of the model or the amount of data, your model will continue to increase in performance, assuming your data is not, poorly labeled or you've got the wrong stuff. As long as you have that squared away, yes, that's.
But that's kind of compute invariant in that if you had 20 million rows today and 50 columns wide, and you were training a neural net, the only difference on a GPU would normally be a newer GPU might be it would train faster.
Right.
Or would you get more performance out of it?
So to get more performance, you usually have to increase the data set size, or so the number of examples, or the model, actual model depth, primarily. So in order to do both of those things, so if you increase the amount of training examples you have, that means your compute's going to scale with the number of training examples that you have, because each example will have to be trained on, or fed through gradient descent. If you have a larger model, the compute for each individual training example will be larger. And that's just going to keep growing, and then you'll get into all sorts of fun problems with model parallelism and stuff like that. But yes, that's, fundamentally those are the two primary knobs that you have to increase, kind of through brute force model's performance. So I will caveat that with, I am a huge believer in make sure your data is clean. I've experienced this in the field. Make sure you've got the right data for the problem, and it's being labeled accurately, because that will, the poorer the quality of the data, the worse the model. The more work you're going to have to do, the more computations you have to do to deal with that. And then also there's, you'll basically, the performance will asymptote, so kind of flatline earlier. So those are just, stuff I've kind of learned through experience doing this stuff. But yeah, fundamentally, to increase the performance of the model, the two primary ways are more data, larger models. Both of those require more compute. So talked about this a little bit already. I think most people are aware the cloud is relatively an expensive luxury when it comes to training, inferencing, if your workload fits there, and they can, provide the resources you need to do, the stuff on the inferencing side of the house. That's pretty great. But definitely for training, it's a huge cost delta between building on an on-premise system and heading to the cloud. And I will always caveat this with, if your cluster is only for 10 DGXs, or 16 or 8 GPU instances up in Amazon, you probably don't really need to worry about it too much yet. But once you start getting into the scale out architectures, you definitely will want to take a look at moving to on-prem, whether it's with us or just other systems. But it's just something to keep in mind.